This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good afternoon everyone. So today we're going to continue looking at Nyquist plots, and in particular how close they get to the critical point -1. Okay, so last time we left off thinking about different ways of measuring how close a Nyquist plot gets to the critical point -1. This is motivated by the fact that we know if the Nyquist plot sits on top of -1, then the closed loop system will have a pair of poles on the imaginary axis at a corresponding frequency. Okay, and we know that if the closed loop system has a pair of poles on the imaginary axis and we kick it, it will respond in an oscillatory fashion, and those oscillations won't even die away, right? So intuitively, if you're very close to the critical point -1, then you will end up with closed loop poles that are close to the imaginary axis. They may be stable, but if you have closed loop poles that are close to the imaginary axis in the sense that the imaginary part of those poles is much larger than the real part of those poles, then when you kick the closed loop, it will respond in a way that's also very oscillatory, okay? And it might take a long time relative to the period of oscillation for those oscillations to die away, okay? So that's why we're interested in seeing how close the Nyquist plot gets to the, how close it is to the critical point -1, all right? As we'll see later on today, there's another reason for being interested in how close the Nyquist plot gets to the critical point -1 from the perspective of how robust the closed loop system will be to modelling errors. Okay, so let's just remind ourselves of the different measures that we looked at last time. One of them has to do with the so-called phase margin. And with the phase margin, we're looking at the point on the Nyquist plot, and remember that the Nyquist plot is really just a polar plot of the so-called open loop transfer function. And we're going to look at the point at which the open loop transfer function has gain 1. Okay, so there will be a frequency, the crossover frequency, where the open loop transfer function has a gain of 1, and the phase margin is the angle between the phase of the critical point -1 and the phase of lambda at that frequency, at the crossover frequency. All right, so we're using the angle to measure how close our Nyquist plot gets to the critical point -1. So that's what phase margin is about. It's about the phase of the open loop transfer function at the crossover frequency. Okay. Another way of measuring how close we are to the critical point -1 is by looking at the frequency associated with the open loop transfer function having a phase that is the same as the phase of the critical point. In other words, a phase of -pi radians. Okay, and then we measure how close the Nyquist plot is to the critical point by asking how much can I scale this up by before I hit the critical point. Okay, these things still make sense when the open loop transfer function has right half plane poles, but if the open loop transfer function has right half plane poles, then in order to get closed loop stability, we will have to have encirclements of the critical point -1. We'll have to have as many anti-clockwise encirclements of the critical point -1 as unstable open loop poles. All right, so the Nyquist plots won't look like this sitting to the right. Okay, they'll have to look like things that will give you anti-clockwise encirclements, right? But there will still be a frequency that corresponds to crossover where the gain is 1, and you'll still be able to measure the angle of the open loop transfer function at that frequency relative to the phase of the critical point -1. as a measure of how close you get, right? So if I've got a Nyquist plot doing this, giving me an anti-clockwise encirclement of -1 because I've got an open loop pole in the right half plane, okay, there will still be a frequency at which, you know, the gain is 1. I can still use that angle as a measure of how close I am, right? I can still use how much I have to scale by to bring the point where the phase of the open loop transfer function is -pi to land on -1 as another measure, okay? But in this case, it might be that scaling it down causes it to sit on the critical point instead of scaling it up, right? So these things can be generalised beyond the case that we're considering here, all right? Another way to measure how close you are is to find the closest point on the Nyquist plot to the critical point -1. We can find that by drawing circles around the critical point -1 and making them bigger and bigger until we finally touch the Nyquist plot, okay? And that will correspond, as we saw last time, to the frequency where the output sensitivity function has peak gain, okay? And that's because each point along here is simply evaluating lambda at a different frequency, okay? So this little vector from -1 to here is 1 plus lambda at the corresponding frequency. So the magnitude of this is the magnitude of 1 plus lambda, right? And so we're identifying here what the smallest that vector can be, right? And it'll correspond not to this frequency, not the crossover frequency in this case, but another frequency, all right? And because the output sensitivity function is just 1 on 1 plus lambda, then if that's where 1 plus lambda is smallest, it's where S will be largest, okay? And so how close we are to the critical point is giving us some kind of indication of how much peaking we might get in the sensitivity function, all right? And if we think about what the sensitivity functions usually look like, okay, if we're looking at the magnitude plot, right, so we're usually going to have the open loop transfer function looking something like this, okay, where we want to have large gain at low frequency, okay, because that will give us low sensitivity of the output to low frequency output disturbances. It will give us low sensitivity of the error signal to low frequency references, okay. Having lambda large at low frequencies makes S small, right? S being 1 on 1 plus lambda. So if lambda is large, S will be small, okay. It also makes T close to 1, all right. At high frequencies, we want low sensitivity of the output to high frequency sensor noise, and that corresponds to making T small, and T, which is equal to lambda on 1 plus lambda, will be small if lambda is small, okay? But where lambda is small, S will be 1, okay? Now, they're easy to design because you just make the gain high at the frequencies where you need S to be small and small where you need T to be small. It's much harder to figure out what happens in between at the so-called crossover frequency, right? So that's where the open loop transfer function crosses the 0 dB line. That's what this is, right? So that's where the gain is 1, okay? And as we've seen before, you can end up with peaking in the sensitivity functions at crossover, right? So the phase margin is giving us, well, not the phase margin, but this peak sensitivity, how close the Nyquist plot, the closest the Nyquist plot gets to the critical point -1 is giving us an indication of how much peaking we can get. Okay, so the further away you are from the critical point -1, the larger eta is here and the smaller the peak in the sensitivity function will be. All right. Why do we want the peaks here to be small? Okay, well, this as a frequency response of a stable transfer function, if the closed loop is stable, is telling us how different frequencies get amplified or attenuated, right, by the system. All right, so if we have a peak here, it means that if I inject energy at this frequency, right, then it's going to get amplified at the output of the plant or at the error signal, okay? And you may not want that, okay? In particular, if we're looking at the transfer function from the reference to the output, right, we know that y and r is t, it's the transfer function lambda on 1 plus lambda. If I'm getting peaking in S, I'm going to get peaking in T because S plus T must equal 1 everywhere, right? We've seen that algebraic constraint before, right? It's obvious that this plus this will give you lambda plus 1 on lambda plus 1. It's always equal to 1. So if S is large, remember this is a complex number, in order for S plus T to be equal to 1, then T will also have to be large in magnitude. So if S peaks up, T will peak up, right? And we know that, you know, when we have R as a step, right, then it doesn't just have energy at 0 frequency, it has energy at lots of different frequencies, right? Most of the energy's at low frequency, but if you put a step into a system that has a transfer function like that, where it peaks up, you'll get oscillations in the response. You get lots of distortion in the output response to a step change in the reference, and that might be why you don't want it to peak up like that. Okay? All right. And in fact, you can, there's an explicit relationship between the gain of the output sensitivity function at the crossover frequency and the phase margin, right? So that's not the same as looking at this, okay? This is finding the peak gain. The peak gain may not occur at crossover, all right? It may occur just after, right, or forward. Depends on what the phase is at crossover, all right? But if it's peaking up, then it's going to probably have, if it has large gain at crossover, right, then it's going to be even larger somewhere else, okay? And it turns out that there's an explicit relationship between the gain of the output sensitivity function at crossover and the phase margin. And you can determine this by just, you know, analysing this little triangle here, okay? That's what lambda is, right, the complex number at the crossover frequency, okay? Our phase margin is the angle of lambda at crossover relative to the phase of the critical point, all right? So the magnitude of the critical point is 1, that's 1, okay? You've got an isosceles triangle. If I draw that dotted line down the middle there, that splits this line in half. We know that the magnitude of the base here is the magnitude of 1 plus lambda at the crossover frequency, because we've chosen that point to be where this is equal to 1. All right, so we've got a little triangle like this, where that's 1, that's half 1 plus lambda, right? That divided by that will be the sine of that angle there. Okay, so there's an explicit relationship between how big the sensitivity function is at crossover and the phase margin. The smaller the phase margin, the bigger this will be. Okay, if this is less than a half, right, then this number will be bigger than 1, and you will definitely get peaking in the sensitivity function at around crossover. Okay, so the phase margin is also going to give you some indication of this when it's small. Okay, but as we saw last time, having good phase and gain margin is not sufficient for having small or no peaking in the sensitivity function, all right? Because we could have a situation like this where we have a Nyquist plot that looks like this, okay? And so this is where the gain is 1, all right? And there's a big angle there, right? This is where the phase is minus pi, and I have to scale that up a lot, right? Or even that point there, still have to scale it up a lot. But if it does this in between, then I can get a large peak in the sensitivity function. All right? So having large phase and gain margins is necessary for having small peaks in the sensitivity functions, but it's not sufficient, right? And the reason it's not sufficient is because this sort of stuff can happen. Okay, but clearly in order to be far away, you need the phase margin to be big and you need the gain margin to be big. All right? So these are the sorts of things that are also easy to read off a Bode plot rather than just looking at a Nyquist plot. All right? So the key thing to remember is that phase margin is about the crossover frequency. It's about the frequency where the open loop transfer function crosses the 0 dB line. Right? Remember, 0 dB is 1, right? Because log of 1 is 0. Okay? So the phase margin can be read off the Bode plot by identifying that frequency where lambda crosses over, okay, and looking at the phase of lambda relative to minus 180 degrees. All right? And we're looking for there to be a positive phase margin, okay? We're looking for this to be above minus 180, okay? It's like having this positive angle here, all right? So you can read that off the Bode diagram very easily, okay? The gain margin is about the frequency where the phase of the open loop transfer function is equal to the phase of the critical point. In other words, minus 180, all right? And the gain margin is about how much I can scale this up or down, depending on whether or not there are unstable open loop poles, in this case where we're assuming that there aren't any, right? Scaling up before the magnitude plot of lambda will sit on the 0 dB line, okay? If I scale lambda by a constant, okay, what's going to happen to the magnitude plot? It's going to move up by the same amount at all frequencies, right? Because the magnitude of this is the magnitude of k times the magnitude of lambda, and if I take the log of that, and I'm taking the log of that, then it's the log of k plus the log of lambda, right? So I'm just adding this, right, which is constant across frequency, to the magnitude part of the Bode plot for lambda, right? So I'm moving it up by the same amount, right? So the gain margin is about how far can I move this up before it sits on the 0 dB line at the frequency where lambda has phase equal to minus 180. Okay? Multiplying by a positive constant k, okay, is not going to change the phase. So it just changes this part, it doesn't change this part. So the frequency doesn't change. But by scaling by k does change the crossover frequency. So by multiplying by a number bigger than 1, you shift everything up on the magnitude plot, and in shifting everything up on the magnitude plot, we've moved the crossover frequency from here to here. We've changed the crossover frequency. And so scaling by gain is effectively, to figure out the gain margin, is setting the phase margin to 0 at the new crossover frequency. Okay? But doing these sorts of things often arises in design. You'll start off and you'll choose the controller, and in choosing the controller you've chosen the open loop shape, and then you make adjustments to it. And a common adjustment to something is just multiplying by a constant gain. So increasing the gain, multiplying by a number bigger than 1, typically shifts, or always shifts, not always, but typically shifts the crossover frequency to the right. And you can see that's what's happening here. When we shift the crossover frequency to the right, we're effectively setting the phase margin to 0. Whereas if we multiplied by a number that was less than 1, right, that would be shifting all these points down by the same amount at every frequency. And so we would get a new curve like this, and multiplying by a constant that's less than 1 decreases the crossover frequency to here. And in this particular case, it would improve the phase margin. Okay? And by improving the phase margin, it is likely that you will decrease the magnitude of the output sensitivity function at crossover, which means you'll probably avoid having large peaks in the sensitivity functions. Okay, so that's the reason I'm showing you these things. It's not so you can, look at something and say, that's the phase margin, that's the gain margin. These things mean something from the perspective of informing design decisions, right? We've just done something, for example, we've given a first shot at a design, and maybe we think that that's a very small phase margin, and it is. It's maybe 10, 15 degrees. So if we just close the loop around this, we might get lots of oscillations in the closed loop response. One way to end up with a closed loop that exhibits less oscillations in its response is to wind back the gain a bit, okay, which will decrease the crossover frequency, increasing the phase margin. But we pay a price. We pay a price because we've decreased the crossover frequency. And by decreasing the crossover frequency, we're reducing the range of frequencies over which T is 1. So we may have gone from a situation like this where we have the bigger peak here, all right, with a wider bandwidth, meaning we can track, in principle, higher frequency signals, right, to something with less gain here, less oscillations in response, but it starts rolling off, okay, at a lower frequency. So we're just moving the distortion that we would get in the step response for the closed loop from being oscillations that might decay fast to something that decays a little bit slower but doesn't oscillate as much. And what's more important depends on the situation. Okay, but you're always making trade-offs like this in design, trading one thing off against each other. So we're trading off speed with which transients decay against how oscillatory the response is. Okay, just by adjusting a parameter that could be part of your controller, right? The gain here that I'm talking about could just be part of your controller. Okay, so this is not about can you look at a Bode diagram and say what the phase and gain margin is without understanding what it means. It means something. Okay, so try to think of it from this sort of perspective. Try to build an understanding for what making adjustments to an open loop transfer function might do in terms of changing the crossover frequency and the effect that that might have on the phase margin and what that might mean for the transient response of the closed loop system. Okay, don't just focus on how do I read these numbers off a plot without understanding anything. All right? Okay, so as I mentioned at the start of the lecture today, another motivation for looking at how close the Nyquist plot gets to the critical point -1 relates to the robustness of the closed loop to modelling error. Right, so we've just looked at it from the perspective of the peaks in the sensitivity functions that you might get around crossover. Now we're going to think of it from a different perspective. Modelling error. So let's start thinking about, well, how could you modelling error? Right? And there's not just one way of doing it, but two common ways of doing it are using an additive perturbation, right? And another common way of doing it is using a so-called multiplicative perturbation. All right? So this is really saying, well, I've got a nominal model for the system, but my real system is an additive perturbation of my nominal model. And you might have some information about the additive perturbation, but not full information. That's what makes it an uncertainty. Okay? You might know how the magnitude of this varies across frequency, but not know what the phase is. Because if you knew both the magnitude and the phase, then you may as well use the sum of the two to be your nominal model. Okay? So this is representing an uncertainty that corresponds to the mismatch between a nominal model and perhaps the real system. And I know something about this, but not everything about it. Okay? This is like a relative error. Okay? If we just multiply this out, so we're saying this is equal to G naught, our nominal model, plus G naught G delta, right? And so really, if I, that's equal to G, right? So I can rearrange that to be G minus G naught, right? That must be equal to G naught G delta. So that's telling me G delta is G minus G naught divided by G naught. Okay, so it's the uncertain bit here, this guy, right? A bit about which you might know something. You might know how its magnitude varies across frequency, but not its phase. These are the sorts of things that are easy to identify from experimental data. It's very easy to look at how magnitudes of numbers change, but keeping track of phase can be a bit tricky, right? So you might have some data from your real system. You have your model, and from the data and model, you can figure out what the magnitude of this is doing, but maybe not the phase. So this is an uncertainty, okay? And it's a measure of relative uncertainty, right? Relative to your nominal model. Okay, so they're just different ways of modelling mismatch between a nominal model and perhaps your real system. Okay? And different ways of doing it. There are other ways to do it. These are not the only ways to do it. Okay, so let's look at some examples of trying to embed parameter uncertainty into modelling errors in these ways. Okay, so let's look at a transfer function form. So the form of these transfer functions is the same. In fact, the poles, two of the poles are the same in all three cases, but the time constant associated with these poles is changing. So that's an example of there being some parameter uncertainty. So you could take your nominal model to be this one, right? And this one is different from this in the sense that the time constant of this pole is 10 instead of 20. And the difference between this and this is that the time constant of this pole is 5 instead of 20. Okay? So, this is the nominal one, right? So this is slower than this one, and this one's faster than this one. Sorry, the red one's the nominal one. Okay, so this is showing what G naught looks like. All right? These are showing what the corresponding additive perturbations are, and just looking at the magnitude of them. So all I'm doing to get this curve, right, is looking at this curve and subtracting away the Bode plot for this guy, right? And that gives rise to that green curve. Whereas this minus this has this curve here, right? You can do the same sort of calculation as this to figure out what the multiplicative modelling error is in terms of how different this is from this and how different this is from this, right? And that gives you these curves here. Right, so I've just calculated these in the way shown here, all right? And what we can observe is that for parameter uncertainty of this kind, that the multiplicative modelling error is most significant at high frequencies. It's more significant at high frequencies than it is at low frequencies. Right? That's what this plot is telling you. The magnitude of the multiplicative modelling error is larger at high frequencies than it is for low frequencies. Whereas the additive perturbation, well, at really low frequencies it's smaller than it is in a mid-range of frequencies, and at high frequencies it's smaller again. Okay? Let's look at this example here, where the parameter uncertainty is in the delay. All right? So here's no delay. Let's say we use a nominal model with no delay. Here we've got delay of 0.4, and here we've got delay of 0.2. Right? So this is what our nominal model's magnitude plot looks like. Okay? This is what the multiplicative modelling error looks like. Again, you can see that it's more significant at high frequency than it is at low frequency. All right? And in this case, the additive uncertainty is such that it's more significant at low frequency than it is at high frequency. Okay? This is just another example again where it's got the same type of parameter uncertainty as the first example, in the sense that the time constants for these two models are different from the time constant in this model. Okay? Here's the nominal model's magnitude plot, right? The corresponding multiplicative uncertainty looks like this, and again, it's more significant at high frequency than it is at low frequency, right? And the additive uncertainty is more significant at low frequency than high frequency. Okay, so all we're trying to do here is embed this parametric uncertainty, if you like, into these forms. Okay, and the way we're going to think about the perturbations, all right, is in terms of their size across frequency. All right. In this case, the perturbations are stable. Okay, but that may not always be the case. Okay, it just turns out to be the case here. All right. Now, for the rest of the lecture, I'm going to focus mainly on the multiplicative uncertainty. All right, because it seems to have the same sort of behaviour in all of the cases considered, right? Whereas it's a bit different for the additive uncertainty, right? The key thing about multiplicative uncertainty is it's typically more significant at high frequency than low frequency. All right. So we may design our system and verify that everything is stable for the nominal model of the plant. Okay, so we have a nominal open loop transfer function lambda naught. And we want to make sure that the closed loop with the perturbed model is also stable. And we can do that via the Nyquist stability criterion, right? And that's easiest when the perturbed open loop transfer function has the same number of right half plane poles as the open loop transfer function. Because if we know this is stable, then this will be stable provided we don't change the number of encirclements of the critical point. Right? Because going from here to here, we haven't changed the number of right half plane poles, so we shouldn't change the number of encirclements of the critical point. Right? If we know this is stable and want to conclude that this is stable. All right? They'll have to make the same number of encirclements of the critical point because they have the same number of right half plane poles. All right? And that will certainly be the case if the additive or multiplicative perturbations are themselves stable. Right? Because, you know, what are we putting in here? We're putting in G plus G epsilon C, and that's just G C plus G epsilon C. All right? And so we have an additive perturbation here that's stable. It's not going to change the number of right half plane poles, and the same for this. Okay? So, all right. How can we make sure that we don't change the number of encirclements of the critical point? All right. Well, let's say the dark blue line here is our nominal open loop transfer function. All right. And the dotted one is the perturbed transfer function. Right. We know that this is making the right number of encirclements of the critical point, and we want to make sure that the dotted line will make the same number of encirclements of the critical point. Right? So, let's have a look. Each point along here corresponds to a different frequency. Okay, so we can think of this point here as being lambda naught j omega, right? And that's why this little vector from here to here is 1 plus lambda naught. And the magnitude of that will be the magnitude of 1 plus lambda naught at the corresponding frequency. Okay. Now, we're going to have the same number of encirclements, right, if we can make sure that this vector here, right, which is really the difference between the perturbed open loop transfer function and lambda naught. Remember, that's a little vector to lambda naught at a frequency. This is a little vector to lambda at the same frequency. So this little vector is the difference between the two, right? And we're looking at the same frequency, all right? So clearly, if this is less than this, then the perturbation that takes us from here to here will not change the number of encirclements of the critical point, which in this case is 0. Right? And if that holds at all frequencies, if the little perturbation, right, from the nominal to the perturbed is always less than the size of this, right, you're not going to change the number of encirclements. Okay? So let's see what this looks like. Well, just write it down. We've got GC minus G0C, right? Well, that's just G minus G0C, okay, which is clearly equal to G epsilon C, the additive perturbation. And if I multiply the top and the bottom by G0, right, you can see that that's the multiplicative perturbation, right, times lambda naught. Okay? So, in order to not change the number of encirclements, I've got to make sure that this vector is smaller in size than this vector. So in other words, if we just focus on the multiplicative perturbation, if we can make sure that G delta lambda naught evaluated at frequency omega is less than this, then we won't change the number of encirclements. Right? All I'm writing down here is I want this to be smaller than this. Okay? So if we rearrange that, what are we saying? Well, we're saying I want G delta times, so the magnitude, this guy here is just equal to what I've written down, right? I want that to be less than this, right? So this should be J omega, all right? So I want the product of the magnitude of G delta and the magnitude of lambda naught on lambda naught to be less than 1. All right? What's this guy here? It's the complementary sensitivity function, or at least its nominal value. I want it to be less than 1. Okay? So where the multiplicative uncertainty, perturbation, is large, I want T to be small so that the product will be less than 1. All right? This is the so-called small gain condition. Okay? And it's all just about saying, I won't change the number of encirclements if the perturbation is smaller than the magnitude of 1 plus lambda naught. All right, you can see that just from this picture. Okay, gives us the small gain theorem. So where this is significant, we want this to be small. Where the multiplicative perturbation is large, we need the complementary sensitivity function to be small. Well, where's the complementary sensitivity function usually small? At high frequencies, right? Where did we see the multiplicative perturbation becoming significant? High frequencies. Okay? You can also think of this in terms of, well, if I know that my multiplicative error is going to be becoming large beyond a certain frequency, then I need to make sure that my crossover frequency is to the left of that, because it will ensure that T, which may peak up before there, will be small. Right? This is T, right? This is G delta. Will be small at frequencies where G delta is large. So having multiplicative model uncertainty puts a limit on the crossover frequency, puts an upper bound on the crossover frequency. Okay, just like sensor noise, where sensor noise starts becoming significant, puts a limit, puts an upper bound on the crossover frequency, right? Because to get low sensitivity at the plant output to sensor noise, we need T to be small. Okay, the same sort of thing goes for multiplicative modelling error. Okay, so these are the sorts of things that stop you making the closed loop system too fast. In order to get less distortion, assuming you don't get peaking up by pushing the crossover frequency to the right, in the output response, we want to push it to the right, right? If I've got a complementary sensitivity function, which remember is the transfer function from the reference to the plant output, if I've got a system that has T looking like that, I'll get a step response that is very slow, right? If I push it out and don't get any peaking, right, then it'll make the response faster. So it might be desirable to push the crossover frequency to the right, right? But if pushing it to the right decreases the phase margin, you'll start getting peaking, okay, which means it'll be fast, but you'll have oscillations. So that's a reason why you might not want to push it too far. Another reason you might not want to push it too far is because in order to satisfy this condition, which is really a robustness condition, you want T to be small where there's significant modelling error, which might be at high frequencies. So what I'm trying to get across here is that design in the end is going to be about balancing these trade-offs. You've got certain things trying to push the crossover frequency further to the right to make things faster, okay, but there are going to be things that stop you from pushing it too far to the right. Like in this example here, pushing it too far to the right made the phase margin tiny, which would lead to oscillations in the response. So there's something stopping you from pushing it too far to the right. Sensor noise stops you pushing it too far to the right. Modelling uncertainty stops you pushing it too far to the right. Okay, so we've got to balance these trade-offs against each other. Okay? All right. Now, performance is not just about stability, and this result is just about stability. Okay? Performance is about how the sensitivity functions are shaped across frequency. And how the sensitivity functions have to be shaped across frequency depends how the external inputs have their energy distributed across frequency. Right? So our reference and our input disturbance and our output disturbance are usually low frequency signals. So the corresponding sensitivity functions that tell us about the sensitivity of the internal signals to those external inputs needs to be small at low frequencies where those signals have high energy, right? Whereas sensor noise might be high frequency, have most of its energy at high frequency, and want the complementary sensitivity function to be small. Okay, so this is about trying to understand how modelling uncertainty changes the shape of the sensitivity functions across frequency, not just how it affects stability. All right? So let's look at it from the perspective of the output sensitivity function. And remember that the output sensitivity function is telling you how sensitive the output signal is to a disturbance at the plant output. It's also telling you how sensitive the error signal is to the reference. Okay, so the transfer function from here to here and the transfer function from here to here are the same. They're given by S0. I don't know what I did then. Whoops. Okay, it's given by S0. Okay, so let's say S0 is the nominal output sensitivity function. So it's the sensitivity function, the transfer function from here to here and here to here that you get when the plant is G0. Okay, and the controller is C. Let's see what happens when we replace G0 by a perturbed version of G0. And let's consider the multiplicatively perturbed G0. Right, so all I'm doing is substituting G0 by G, and G is 1 plus G delta times G0. So I'm just substituting it in. If you take out the factor 1 plus G0C, which you get from 1 times that, out the front, you get this form here. Okay, That is our nominal output sensitivity function, and this is a perturbation that multiplies it to give us our perturbed output sensitivity function. Ideally, we would like this to be equal to the thing that we got on the basis of our nominal model, which is the thing that you would use for design of C. Right? Well, when is the multiplicative perturbation not going to change the output sensitivity function? Well, it's not going to change the output sensitivity function if this is approximately equal to 1 at all frequencies, because then I'm just multiplying by 1. And I don't just mean 1 as in size, I mean 1, the number 1 plus j 0, so it doesn't change the phase, doesn't change it. How can I make this, which is S delta, how can I make this equal to 1? Well, I can make this equal to 1 by making this 0, very small. Okay? So our nominal and perturbed performance will be similar if S delta is equal to 1, and S delta being equal to 1 just requires T, the complementary sensitivity function, times the perturbation to be much, much smaller than 1. Because when that holds, this is equal to 1. And so our perturbed sensitivity will be the same as our nominal one. Right? So it's just making this condition even stronger. Right? This has required it to be less than 1. Right? And that's all you need in order to retain stability. And it's important to realise that it's just a sufficient condition. Right? I'm potentially being very conservative here because I'm only looking at the magnitude of these things. I'm not looking at the phase. Right? So the perturbation with this size could be in any of these directions. And clearly when it's moving this way, it's actually pushing us further away. Right? But I'm considering the worst case where the perturbation pushes you directly towards the critical point -1. Right? But to know what's happening, I would need to know the phase of the perturbation. But if I know the phase of the perturbation and the size of the perturbation, I know everything about it and it's not uncertain anymore. All right? So this is potentially conservative, right, as a stability result. But to apply it as a stability result, you just need it to be less than 1. But if I know that that product is much, much less than 1, then I know the perturbed closed loop will behave very much like the nominal closed loop. Okay, so how do we achieve that? Well, we just make sure that where the modelling uncertainty is significant, we have complementary sensitivity function small. So, you know, I can make it really small by making sure my complementary sensitivity function rolls off back here. And if I make it roll off back here, then the product of these two things, which will just be the sum of them, will be very, very small. Okay? All right, let's just finish off with a quick example. All right, where you've got a plant with a pole at -1 and a pole at -2. Okay, our requirements are that we need to track a unit step reference. Okay, and we know that we'll be able to do that if we design our open loop transfer function to have infinite gain at 0 frequency. Right, we've seen in the error analysis, you know, analysis of the error signal way back here. I don't know where it is now. Where is it? Okay, if we make the open loop sensitivity, open loop transfer function have infinite gain at 0 frequency, right, we'll get 0 steady state error for a step. All right, how can we make the open loop transfer function have infinite gain at 0 frequency? Well, we just put a pole at s equals 0 into the controller transfer function. There it is there. Okay? We're cancelling out the stable poles with these two zeros. That's okay, you can have pole zero cancellation as long as they're stable pole zero cancellations. The big no-no is unstable pole zero cancellations. And the reason is that any pole zero cancellation between the plant and the controller, or any pole that's cancelled between the plant and the controller will be a pole of one of the sensitivity functions, right? Because any cancelled poles here appear as a factor of the characteristic polynomial, right? So if you cancel an unstable pole, right, then one of your sensitivity functions will be unstable. We don't want that. But you can cancel a stable pole. You just have to live with the fact that one of your sensitivity functions will have transients that don't decay any faster than e to the minus t. Let's say that's okay. All right? And so we cancel them out. All right? And then the rest of the compensator is this. Okay? So this guy is about making sure that we have infinite gain at DC so that we can get zero steady state error for a step reference. All right? Now, what else have we got acting on the system? We've got an input disturbance, a plant input disturbance. All right? Now, we don't know what it is exactly because we don't know its gain, its size, and we don't know its phase, right? So it's uncertain, if you like, and we can use these external input signals to represent uncertainty, right? This is an uncertain input signal of unknown size, unknown phase, but known frequency. Right? And we can exploit the fact that we know the frequency in the design of the controller in order to get perfect rejection of the input disturbance in steady state. All right? By doing the same thing as we did for the reference. All right? As we'll see in a few lectures' time, by having poles on the imaginary axis at a frequency consistent with the frequency of an input, okay, we will get perfect rejection of that input. All right, so the frequency here is 1, and so we're putting a pole at j and minus j. What that does, it makes the gain of the open loop transfer function infinite at that frequency, which puts this perfect notch in the corresponding closed loop sensitivity function, meaning energy injected here at this frequency here gets mapped to 0, right, in steady state. Okay, so it's very similar to putting the pole at s equals 0 in order to get 0 error for a step input. Okay. These two here are about increasing the phase at crossover, right? So the red shows what the open loop transfer function is, the product of this and this, okay? So you can see that really the open loop transfer function looks like, once we've cancelled the pole at s equals minus 1 and s equals minus 2, it equals a gain, s plus 3, s plus 5, s squared plus 1, s plus 100, okay? So these guys have an effect first, right? And you can see that this is giving us the infinite gain at low frequency. This guy is giving us the infinite gain at 1 radian per second. The phase of an integrator is minus 90, right? And then the phase around the frequency 1 of this quickly changes from 0 to minus 180, which we're adding to minus 90. So it pushes us down here. All right? Now this is going to cross over. And where it crosses over, we want the phase to be above minus 180. Right? So that we have a positive phase margin. To get that, we need, 180 is here. We need to have two zeros that add phase. What are zeros? If I look at the phase plot of a 0, right, what happens? It starts off at 0 and then it goes up to pi and 2, to 90, right? That's Z, that's 0.1 Z, that's 10 Z, that's pi and 4, right? So having a 0 gives you positive phase. It pushes the phase up, all right? And we're using it in this case to ensure that at the crossover frequency, we're going to push have a phase that is above minus 180. All right? Now, how have we chosen the crossover frequency? We've chosen the crossover frequency to be lower than the frequency where the multiplicative modelling error becomes significant. So this dotted line here is showing where the multiplicative modelling error becomes significant. It's more significant at high frequency than it is at low frequency. We know by the small gain condition that we want